Tonight, we're going to explore one of the most audacious missions humanity has ever attempted. A spacecraft the size of a small car, wrapped in a heat shield barely 4.5 inches thick, sent on a deliberate collision course with the closest star to Earth. Not to orbit safely at a distance, not to study the sun from afar like every previous solar mission, to dive directly into its outer atmosphere, to touch a region where temperatures soar past 2 million degrees Fahrenheit, to go where no machine built by human hands has ever survived. And what it recorded down there in the burning corona of our star has left some of the most respected solar physicists in the world struggling to explain what they're looking at. The Parker Solar Probe launched on August 12, 2018, from Cape Canaveral aboard a Delta IV Heavy rocket. Its mission was unprecedented in the history of space exploration. Approach the sun closer than any object humans have ever built, pass through the corona, sample the solar wind at its source, measure the magnetic fields, the particles, the plasma waves in a region that until that moment had only been studied from afar through telescopes and remote sensing. And on December 24, 2024, after 21 orbital passes and 7 gravity assists from Venus, Parker reached its closest approach. Just 3.8 million miles from the sun's surface, traveling at 430,000 miles per hour, the fastest any human-made object has ever moved. But here is what shocked the scientific community. The data Parker began sending back didn't match the models, not slightly, not in minor details that could be explained away. The fundamental picture of how our sun works, how its corona heats up, how the solar wind accelerates, how magnetic fields behave near the surface of a star, all of it began to unravel. Parker recorded phenomena that no theory had predicted. Strange S-shaped twists in the magnetic field, structures so abrupt and so violent that physicists initially thought they were instrument errors. A region near the sun where the dust that fills the inner solar system simply vanishes, as if something is sweeping it clean. Solar wind streams that accelerate to speeds the equations say should be impossible, and measurements so anomalous that, years later, NASA scientists are still careful about how they describe them in public statements, still hedging, still using phrases like further analysis is required, and the mechanism remains unclear. There are things Parker Solar Probe has detected that have not been given a definitive scientific explanation, not because anyone is hiding them, but because nobody yet knows what they mean. And that gap between what was recorded and what can be explained is where the real story lives. Before we get started, if you find yourself drawn to the mysteries that lie at the edge of human understanding, take a moment to like this video or subscribe to the channel. It is a small action, but it helps this work reach more people who share that curiosity. And tell us in the comments where you are watching from tonight. We love seeing how far this story travels. Now, let's begin. The sun is the most studied object in astronomy. It has been observed continuously for thousands of years, sketched by ancient astronomers, photographed by Galileo's telescope, monitored by dozens of spacecraft from Skylab to the Solar Dynamics Observatory to Soho. We know its mass, its diameter, its luminosity, its rotation rate. We have mapped its surface features, recorded its 11-year activity cycle, traced the paths of its sunspots across its face. By every measure, the sun should be the body in our solar system about which we know the most. And yet, when scientists sat down to design Parker Solar Probe in the early 2000s, they had to admit something embarrassing. Some of the most basic questions about how the sun actually works had no satisfying answers. The corona, the outer atmosphere of the sun, is millions of degrees hotter than the surface beneath it. That makes no physical sense. Imagine a campfire that gets hotter the farther you move away from the flames. Imagine standing in a room where the air 10 feet from a heater is colder than the air 30 feet away. Every principle of thermodynamics says heat should flow from hot to cold, that the corona should be cooler than the surface, not hundreds of times hotter. But it is. And for over 70 years, since the corona's true temperature was first measured in the 1940s, no one has been able to definitively explain why. The solar wind is the constant stream of charged particles flowing outward from the sun, the same wind that Voyager later measured all the way to the edge of the heliosphere. But where does the solar wind actually originate? How does it accelerate from nearly motionless plasma at the sun's surface to speeds of over 1 million miles per hour by the time it passes Earth? What gives it that energy? Again, theories existed. Mathematical models had been refined for decades. But the precise mechanism, the actual physical process that turns hot plasma into a supersonic wind, remained one of the great open questions in solar physics. Eugene Parker himself, the physicist after whom the spacecraft was named, had predicted the existence of the solar wind back in 1958. He published a paper in the Astrophysical Journal arguing that the corona was too hot to be gravitationally bound to the sun, that it must be flowing outward continuously. The scientific community initially rejected his theory. Reviewers called the idea ridiculous. The paper was nearly rejected outright. Only the intervention of the editor, Subramanian Chandrasekhar, allowed it to be published. Within 4 years, spacecraft measurements confirmed Parker had been right. The solar wind was real. But the question of how it was accelerated, how the corona heated, how magnetic fields connected the sun to its expanding atmosphere remained unanswered for the next 60 years. The only way to find out was to go there, to send a spacecraft directly into the corona, into the region where the solar wind is born, where the heating happens, where the magnetic fields originate. To take measurements not from millions of miles away, but from inside the process itself. That was the only way to settle the question. And until the engineering existed to build a spacecraft that could survive such an environment, the question would remain open. Parker Solar Probe was the answer to that challenge. A spacecraft designed from the ground up to do what no machine had ever done. To enter the sun's atmosphere. To survive temperatures that would melt steel. To send back data from a region that, for all of human history, had been completely inaccessible. And what it found in there is rewriting our understanding of stars. Not just our sun, every star in the universe. In the sections that follow, we are going to walk through this story carefully. The history of how we got here, the engineering miracle that made the mission possible, the discoveries Parker has made, one by one, and the phenomena it recorded that, even today, the people who built the mission cannot fully explain. By the end of tonight, you will understand why some scientists believe Parker Solar Probe has uncovered something fundamental about the nature of our star, something we were not prepared to find. The idea of a spacecraft that could touch the sun did not begin with Parker Solar Probe. It did not begin in the 2000s or even in the 1990s. It began in 1958, the same year Eugene Parker published his theoretical paper predicting the solar wind. That year, the newly formed National Academy of Sciences released a report identifying the most important space missions humanity should attempt in the coming decades. Buried in that list, alongside lunar landings and planetary probes, was a proposal that seemed almost like science fiction at the time. A solar probe, a mission that would fly directly into the sun's outer atmosphere and sample it from the inside. It would take 60 years for that idea to become reality. 6 decades of failed proposals, abandoned designs, technological dead ends, and budget cuts. The mission was almost cancelled more times than anyone can easily count. It went through dozens of iterations, dozens of names, dozens of design teams. And every single time the project came close to launch, the same fundamental problem stopped it: the heat shield. Nobody knew how to build a material that could survive what the spacecraft would have to endure. In the 1960s, the proposal was known as the Solar Probe. The original concept called for a spacecraft that would use a gravity assist from Jupiter to slow itself down, falling toward the sun on a trajectory that would bring it within just a few solar radii of the surface. The mission would have lasted years, with most of that time spent traveling to Jupiter and back. The science would have been extraordinary, but the engineering was impossible. The materials needed to protect the spacecraft from solar radiation did not yet exist. Carbon composites were still in their infancy. The thermal modeling required to predict how the spacecraft would behave in the corona was beyond the capabilities of the computers of that era. The mission stayed on paper. In the 1970s and 80s, while Voyager was exploring the outer planets, solar physicists kept pushing for their own grand mission. They wrote proposal after proposal, studied trajectory after trajectory, The mission was renamed Star Probe, then Solar Probe again, then the Solar Probe Plus. Each iteration tried to solve the heat problem in a different way. Some proposed massive radiator fins that would dump heat back into space. Others proposed cooling systems that would circulate fluids through the spacecraft. Some suggested the probe should make only a single brief flyby, sampling the corona for minutes before retreating to a safer distance. None of the designs were ever approved for development. The technology simply was not ready, and the cost estimates were always too high. In the 1990s, NASA briefly approved a mission called the Solar Probe under its Outer Planets and Solar Probe program. The mission was designed to use a Jupiter gravity assist to fall toward the Sun, passing within 4 solar radii of the surface. But the program was cancelled in 2003 due to budget constraints. The Jupiter gravity assist itself was a problem. Sending the spacecraft out to Jupiter first meant a long, expensive cruise phase. It meant the spacecraft would have to survive years in deep space before its primary mission could even begin. And it meant the probe would arrive at the Sun moving extremely fast, with only a brief window to take measurements before flying past. The breakthrough came in the early 2000s, when a team of mission designers at the Johns Hopkins University Applied Physics Laboratory proposed a completely different approach. Instead of using Jupiter to slow the spacecraft down, they would use Venus to do it. Multiple gravity assists from Venus over a period of years would gradually shrink the spacecraft's orbit, pulling it closer and closer to the Sun with each pass. This trajectory had several enormous advantages. It eliminated the need for a long cruise to Jupiter. It allowed the spacecraft to make multiple close passes of the Sun, each one closer than the last. And it could be accomplished with a smaller, lighter spacecraft, one that did not need to carry the fuel for a journey to the outer solar system. The mission was approved in 2009 under the name Solar Probe Plus. It was renamed Parker Solar Probe in 2017, becoming the first NASA spacecraft to be named after a living person. Eugene Parker, then 90 years old, attended the launch in 2018. He had waited 60 years to see his prediction tested in the place where it originated. He died in 2022, having lived just long enough to see the spacecraft begin its first close passes and confirm some of his theoretical work. The mission design was elegant in its simplicity. Parker would launch on a Delta IV Heavy rocket, one of the most powerful launch vehicles in the American fleet, augmented with a Star 48 upper stage. The combination would give Parker more energy at launch than any spacecraft ever sent from Earth. It needed that energy not to fly outward, but to fly inward. Reaching the Sun is harder than leaving the solar system entirely. Earth orbits the Sun at roughly 67,000 miles per hour. To fall toward the Sun, a spacecraft has to cancel out most of that orbital velocity. Otherwise, it just keeps orbiting at the same distance, like Earth does. This is the counterintuitive truth of solar physics. Reaching the Sun is energetically more demanding than reaching almost anywhere else in the solar system. You do not just point a rocket at the Sun and fire. You have to give the spacecraft enough energy to undo Earth's orbital motion, and then carefully shape its trajectory using planetary gravity to bring it closer and closer to the star at the center of everything. Parker's 7 Venus flybys would do exactly that, each one stealing a bit of orbital energy from the planet and using it to tighten the spacecraft's loop around the Sun. The trajectory was calculated to bring Parker progressively closer with each pass. The first close approach in November 2018 brought the spacecraft within 15 million miles of the Sun. Each subsequent pass brought it closer. By December 2024, Parker would reach its planned closest approach of 3.8 million miles, well inside what scientists call the Alfvén critical surface, the theoretical boundary that marks the true edge of the solar corona. That made Parker, in a very real sense, the first spacecraft to touch the Sun. The instruments aboard the spacecraft were specifically designed to answer the questions that had eluded solar physicists for decades. There were 4 instrument suites: FIELDS, which would measure electric and magnetic fields, plasma waves, and radio emissions. S-letter 298 is named with a stylized sun symbol, which would measure energetic particles across a wide range of energies. SWEAP, the Solar Wind Electrons Alphas and Protons Investigation, which would directly sample the solar wind plasma. And WISPR, the Wide Field Imager for Solar Probe, which would take pictures of the corona and the solar wind structures that Parker flew through. Each instrument represented years of development. SWEAP's Solar Probe Cup, for example, had to be designed to actually extend beyond the protective shadow of the heat shield, sticking out into the full glare of the sun to scoop up plasma directly. It would experience temperatures hot enough to melt most metals. It was built from a combination of titanium, zirconium, niobium, and molybdenum, with sapphire crystal insulators chosen specifically because they could withstand both the heat and the intense electromagnetic environment near the sun. The cup itself glowed red-hot during close approaches, and yet it had to keep working, measuring the density and velocity of solar wind particles flowing past at supersonic speeds. But none of this would have mattered without the heat shield. The thermal protection system, as engineers called it, was the single piece of technology that made Parker's solar probe possible. Without it, the entire mission was just another paper study, gathering dust in an archive somewhere. And the heat shield itself, when it was finally built and tested, turned out to be one of the most remarkable engineering achievements in the history of spaceflight. Before Parker Solar Probe launched in 2018, solar physics had developed a sophisticated and confident picture of how our star worked. Generations of scientists had built models of the sun based on telescopic observations, spectroscopic measurements, and data from a fleet of spacecraft that had studied the sun from a safe distance. The Solar and Heliospheric Observatory, known as SOHO, had been watching the sun continuously since 1995. The twin stereo spacecraft had been taking three-dimensional images of solar storms since 2006. The Solar Dynamics Observatory had been recording high-resolution video of the sun's surface and lower atmosphere since 2010. Combined, these missions had produced more data about the sun than any other object in space. From all of this, scientists had constructed what they believed was a reasonably complete picture of the sun's structure and behavior. The sun, they understood, is a giant ball of plasma, about 860,000 miles in diameter, composed mostly of hydrogen and helium. At its core, temperatures reach roughly 27 million degrees Fahrenheit, and pressures are so immense that hydrogen nuclei fuse into helium, releasing the energy that powers everything. That energy slowly works its way outward through the radiative zone, where it takes hundreds of thousands of years to migrate from the core to the surface. Above the radiative zone lies the convection zone, where massive currents of hot plasma rise and fall like water boiling in a pot. The visible surface of the sun is called the photosphere. This is what we see when we look at the sun, though we should never look directly. The photosphere has a temperature of about 10,000 degrees Fahrenheit. It is where sunspots appear, dark regions where intense magnetic fields suppress the upward flow of heat. Above the photosphere lies the chromosphere, a thin layer of plasma that becomes visible only during total solar eclipses, glowing reddish around the moon's silhouette. And above the chromosphere lies the corona, the sun's outer atmosphere, a vast region of extremely thin plasma that extends millions of miles into space. Here is where the conventional understanding ran into the problem that had haunted solar physics for 70 years. The corona is hot, not warm, not slightly elevated, but extraordinarily hot. Temperatures in the corona range from 1 million to 3 million degrees Fahrenheit. By comparison, the photosphere beneath it is around 10,000 degrees. The corona is somewhere between 100 and 300 times hotter than the surface from which it originates. This is the coronal heating problem, and it has been called one of the great unsolved mysteries of physics. The reason it is a mystery comes back to basic thermodynamics. Heat naturally flows from hotter regions to cooler regions. A stove burner heats a pot of water because the burner is hotter than the water. Sunlight warms the earth because the sun is hotter than the planet. Energy moves in one direction, from high temperature to low temperature, and the closer you get to the source of heat, the hotter it should be. But the corona violates this. The further you move from the sun's surface, The hotter the plasma becomes, at least until you get a few solar radii out, where the temperature finally begins to drop. It is as if the sun has a layer of fire floating above it, hotter than the surface itself, kept burning by some mechanism nobody could identify. By the early 2000s, theoretical physicists had narrowed the explanations down to two main candidates. The first was wave heating. The idea was that magnetic and acoustic waves generated by turbulence in the convection zone propagate upward through the chromosphere and into the corona, where they dissipate their energy and heat the plasma. The waves would be like ripples traveling along the magnetic field lines that thread through the sun's atmosphere, carrying energy from the noisy interior up into the quieter regions above. When the waves reached the corona, they would lose coherence, break down into turbulence, and deposit their energy as heat. The second candidate was magnetic reconnection. The sun's atmosphere is filled with magnetic field lines, twisted and braided by the constant churning of the plasma beneath. Occasionally, oppositely directed field lines come into contact, and when they do, they snap and reconnect into new configurations, releasing enormous amounts of energy in the process. This is what powers solar flares, the most violent events in our solar system. The theory was that countless smaller reconnection events, far too small to see from Earth, but happening continuously across the entire surface of the sun, could collectively deposit enough energy to heat the corona to its observed temperatures. These were sometimes called nanoflares, miniature versions of the giant flares that occasionally erupt and disrupt radio communications on Earth. Both theories had supporters. Both had supporting evidence from various observations. Neither had ever been definitively confirmed. The reason was simple. From Earth, or even from spacecraft orbiting near Earth, the corona is too far away to resolve the kind of fine-scale structures that would distinguish between the two theories. You can see large features. You can measure average temperatures. You can spot major flares. But the small-scale physics, the actual mechanism by which energy is deposited into the plasma, was hidden in the unresolved blur of distance. To see it, you would have to go there. The solar wind presented a similar puzzle. By the early 2000s, scientists knew the solar wind existed. They knew it flowed continuously from the sun in all directions. They knew it came in two main varieties. A slow solar wind, moving at around 250 miles per second, originating from regions near the sun's equator, and a fast solar wind, moving at around 500 miles per second, originating from coronal holes near the sun's poles. They knew it carried the sun's magnetic field outward, shaping the entire structure of the heliosphere. They knew it eventually slowed down at the termination shock and stopped at the heliopause, billions of miles from the sun. What they did not know was how it was accelerated. Hot plasma at the base of the corona is moving slowly, not enough to escape the sun's gravity. Yet by the time that plasma is a few solar radii out, it is moving fast enough to escape into interstellar space. Something happens in that region, something that converts thermal energy into directed motion, something that gives the solar wind the kick it needs to leave its parent star. The acceleration mechanism was assumed to be related to whatever heated the corona. If the corona is being heated by waves, those same waves might be pushing the plasma outward. If it is being heated by nanoflares, the magnetic reconnection events might also be propelling material away from the sun. But again, the details were guesses, refined over decades into mathematical models, but never confirmed by direct observation. There was a third area where conventional wisdom had built up a confident picture: the magnetic field structure of the sun's atmosphere. The sun's magnetic field is generated deep in the interior by the motion of charged particles in the convection zone, a process called the solar dynamo. The field lines emerge from the surface, loop through the corona, and extend outward into space, where they get carried along by the solar wind. The field lines were assumed to be relatively smooth on large scales, with most of the irregularities confined to small turbulent structures near the surface. The Parker spiral, named after Eugene Parker himself, described how the field lines spiral outward as the sun rotates, like water from a rotating sprinkler. This was the picture Parker solar probe was going to test: a corona heated by some unknown mechanism, possibly waves, possibly nanoflares. A solar wind accelerated by some related process, possibly through pressure gradients, possibly through wave-driven momentum transfer. A magnetic field structure that was generally smooth on large scales, with turbulence confined to small features. Scientists were confident the basic picture was right. They expected Parker to fill in the details, to resolve the small ambiguities, to confirm one theory or the other. They expected the spacecraft to clarify what they already mostly understood. They did not expect Parker to make them question everything. Parker Solar Probe completed its first close approach to the Sun on November 5, 2018. The spacecraft passed within 15 million miles of the solar surface, closer than any human-made object had ever been. The instruments worked perfectly. The heat shield performed exactly as designed. The data began streaming back to Earth in early 2019, and the science team gathered at the Johns Hopkins Applied Physics Laboratory in Maryland to begin the analysis. They expected to find confirmation of long-standing models. They expected the data to fit neatly into the framework solar physicists had spent decades building. What they found instead was the first crack in that framework. The data showed something nobody had predicted. The magnetic field, instead of behaving in the relatively smooth, well-organized way the models suggested, was full of sudden, violent reversals. The field lines would point in one direction, and then within seconds, they would whip around almost 180 degrees and point in the opposite direction. Then, just as suddenly, they would snap back to their original orientation. These reversals were not gradual. They were not small. They were dramatic, abrupt, and they were happening constantly. Some lasted only seconds. Some lasted minutes. They came in bursts and clusters. They appeared throughout the regions Parker was sampling, not just in isolated patches. The science team initially thought something was wrong with the instruments. The FIELDS investigation, the suite of sensors designed to measure electric and magnetic fields, had been carefully calibrated and tested. But measurements this extreme, this rapid, this violent, looked like they could be artifacts, glitches, errors in the data pipeline. So the team did what good scientists do when faced with surprising results. They went back and checked everything. They reviewed the instrument calibrations. They examined the raw data for signs of contamination. They compared measurements from different sensors. They ran simulations to see if the patterns could be explained by anything other than real magnetic field reversals. After months of analysis, the answer became unavoidable. The reversals were real. The team gave them a name. They called them switchbacks because the magnetic field lines were folding back on themselves like a hairpin turn on a mountain road. A switchback would begin with the magnetic field pointing in its expected direction, generally outward from the Sun. Then the field would suddenly bend, twist, and momentarily point inward, back toward the Sun. Then it would unbend and return to its outward orientation. The entire event might take a few seconds or a few minutes, but the shape was unmistakable. The field was making sharp, S-shaped curves in the plasma that flowed outward from the corona. This was not in any model. No solar physicist had predicted that the magnetic field near the Sun would behave this way. The standard picture had the field lines extending outward more or less smoothly, with turbulence and irregularities at smaller scales, but nothing like these sudden, violent reversals. The discovery raised immediate questions. What was causing the switchbacks? Where were they forming? How were they being generated? And why had no theory predicted them? The early hypotheses were tentative. Some scientists suggested the switchbacks were caused by small-scale magnetic reconnection events near the Sun's surface, the same nanoflares that had been proposed as a possible coronal heating mechanism. The idea was that when magnetic field lines reconnect, they snap and release energy, and that snap could send a kink propagating outward through the plasma, eventually appearing as a switchback when Parker flew through it. Other scientists proposed that the switchbacks were generated higher up in the corona by interactions between different streams of solar wind moving at different speeds. Still, others suggested they might be related to a phenomenon called interchange reconnection, where open and closed magnetic field lines exchange configurations near the boundaries of coronal holes. None of the explanations were fully satisfying. Each one could account for some features of the switchbacks, but not others. The frequency was wrong for one theory. The size distribution was wrong for another. The locations did not match a third. Years later, even with data from multiple close approaches, the origin of the switchbacks remains an active area of research. There is no consensus. There is no settled answer. But the switchbacks were not the only anomaly Parker found on those first close passes. The spacecraft also detected something even stranger about the solar wind itself. As Parker moved closer to the sun, the science team had expected the solar wind to slow down. After all, the wind has to be accelerated from rest at the surface up to its final speed. So closer in, it should be moving more slowly. The models predicted a gradual deceleration as Parker approached the sun, with the wind speed dropping smoothly as a function of distance. That is not what happened. The solar wind near the sun was moving faster than the models predicted. Not slightly faster, significantly faster. And it was not just the speed that was off. The wind was also rotating, swirling around the sun in the same direction as the sun's rotation. This was expected to some extent, since the sun's rotation drags the wind along as it leaves the surface. But the magnitude of the rotation was several times larger than any model had forecast. The wind was spiraling outward in a much tighter, much more energetic pattern than anyone had imagined. This had implications for one of the deepest questions in stellar physics. Stars lose angular momentum over time through their stellar winds. As particles fly outward, they carry rotational energy with them, gradually slowing the star's spin. This process, called magnetic braking, is fundamental to how stars evolve. It determines how fast they rotate, how their magnetic fields evolve, how their atmospheres behave. The amount of angular momentum carried away by the solar wind affects how the sun has slowed over its 4.5 billion years of life, and it affects how all stars in the universe evolve over cosmic time. Parker's measurements suggested that the angular momentum loss was happening more efficiently than thought, which meant the entire theoretical framework for stellar spin-down might need revision, not just for our sun, but for every star. There was also the matter of dust. The space between the sun and Earth is not empty. It is filled with a faint, diffuse cloud of microscopic dust particles, the leftover debris of comets and asteroids that have passed through the inner solar system over billions of years. This dust is so fine that on Earth, you can sometimes see it as the zodiacal light, a faint glow along the ecliptic visible on dark nights before sunrise or after sunset. The dust extends throughout the inner solar system, getting denser closer to the sun, where the gravitational pull concentrates it. Or so the models said. Parker's WISBR camera, which was designed to take images of the corona and the solar wind, began capturing pictures of the inner solar system from a vantage point no spacecraft had ever occupied. And in those pictures, the science team noticed something strange. As Parker got closer to the sun, the dust started thinning out. Not gradually, not slightly. There was a region where the dust simply was not there. A clear zone, where the density of microscopic particles dropped to nearly zero. The clear zone began at about 5 million miles from the sun, well within Parker's orbital range, and it extended down toward the surface. Models had predicted that dust should be present throughout this region, slowly evaporating in the heat as it spiraled inward, but still present in measurable quantities. Parker found a void. The dust was gone, swept away by something. The likely explanation involved the intense radiation pressure near the sun, which can blow small particles outward, combined with the heat that vaporizes them entirely. But the sharpness of the boundary, the way the dust just suddenly stopped at a specific distance, was unexpected. It suggested processes that had been theorized but never directly observed, now confirmed in a way that raised as many questions as it answered. These were the first cracks, the switchbacks. The faster, more energetic solar wind, the disappearing dust. Each one was a hint that the models had been incomplete, that the sun was doing things scientists had not anticipated. And Parker had only just begun. The closest approaches were still years away. The deepest mysteries had not yet been touched. To understand how Parker Solar Probe could survive what no machine had ever survived before, you have to understand the heat shield. Everything else about the spacecraft, the instruments, the The trajectory, the discoveries it would make, depended on a single piece of engineering. A disc of carbon composite, 8 feet wide and 4.5 inches thick, mounted on the sun-facing side of the spacecraft. Without it, Parker would have lasted about 30 seconds in the environment it was designed to enter. With it, the probe could sit just 3.8 million miles from the surface of a star and continue operating as if nothing unusual were happening behind it. The shield is officially called the Thermal Protection System, or TPS. It was designed and built by the Johns Hopkins Applied Physics Laboratory in Maryland, with contributions from research teams across the country. It looks deceptively simple from the outside. A flat hexagonal disc, painted bright white on the sun-facing surface. Behind that white coating lies the heart of the system, 2 thin layers of carbon-carbon composite sandwiching a thick core of carbon foam. The entire structure weighs just 160 pounds. By aerospace standards, it is remarkably lightweight for what it has to do. The principle behind the shield is simple to describe and almost impossibly difficult to engineer. The sun-facing surface absorbs the intense solar radiation and heats up to extreme temperatures, around 2,500 degrees Fahrenheit at closest approach. Behind the shield, in the shadow it casts, the spacecraft body remains at near room temperature, around 85 degrees Fahrenheit. The shield does not block the heat. It cannot, because the heat is real and there is nowhere for it to go. Instead, the shield manages the heat. It absorbs energy on one side, conducts as little of it as possible to the other side, and radiates the rest back out into space as infrared light. The carbon foam at the core of the shield is the key. It is an extraordinary material, 97% empty space by volume, made of microscopic carbon struts arranged in a porous lattice. Carbon foam has very low thermal conductivity, meaning heat does not flow through it easily. It also has very low density, which keeps the weight manageable. And critically, carbon retains its strength at extreme temperatures. Most metals would melt or weaken at the temperatures Parker's shield endures. Carbon does not. It can stay solid and structurally sound at temperatures well above 3,000 degrees Fahrenheit, which is why the same material is used in the brake discs of high-performance racing cars and in the leading edges of hypersonic vehicles. The white coating on the sun-facing surface is another piece of careful engineering. The material is a specially formulated alumina-based ceramic, sprayed onto the carbon-carbon outer layer in a thin, uniform film. Its purpose is to maximize the shield's reflectivity. White surfaces reflect more sunlight than dark ones, which means less energy is absorbed in the first place. The coating also has high emissivity in the infrared, which means it radiates absorbed heat away efficiently. The combination of high reflectivity and high emissivity is what allows the shield to maintain a stable temperature instead of continually heating up over time. Whatever energy gets absorbed has to be re-radiated, or the shield would melt. But the engineering challenges did not end with the shield itself. The shield had to be aligned perfectly to face the sun at all times. Even a small misalignment would expose part of the spacecraft body to direct sunlight, and that part would quickly fail. To maintain proper orientation, Parker uses a set of small solar limb sensors mounted at the edges of the shield. These sensors detect the position of the sun's edge relative to the shield, and if the spacecraft drifts even slightly out of alignment, the attitude control system fires small reaction wheels and thrusters to correct the orientation. The system operates autonomously. Round-trip communication with Earth takes too long for human operators to intervene if something goes wrong. The spacecraft has to defend itself in real time. The solar panels presented their own challenge. Parker needs electrical power, which means solar panels. But solar panels close to the sun would generate enormous amounts of heat and would be damaged by the intense radiation. The solution was a system of articulating solar arrays that retract and extend depending on the spacecraft's distance from the sun. When Parker is far from the sun, the arrays extend outward to capture as much sunlight as possible. When Parker is close to the sun, the arrays retract behind the heat shield, exposing only small portions of the cells to direct sunlight. The cells themselves are cooled by a fluid loop system that circulates deionized water through the panels, and into a radiator that dumps the heat back into space. The water is kept liquid by a system of heaters when the spacecraft is far from the sun, and by the cooling system when the spacecraft is close. It is an active thermal management system operating in one of the most thermally extreme environments any machine has ever faced. Once the spacecraft was built and ready, the next challenge was getting it to the sun. As mentioned in the earlier section, reaching the sun is harder than reaching the outer planets. Earth orbits the sun at about 67,000 miles per hour, and to fall toward the sun, the spacecraft has to lose most of that velocity. The Delta IV Heavy rocket, with its added Star 48 upper stage, gave Parker the largest launch energy ever provided to a spacecraft. But even that enormous boost was not enough on its own. The trajectory required 7 gravity assists from Venus, each one removing a bit of orbital energy and pulling Parker closer to the sun on each subsequent pass. The Venus flybys are themselves remarkable feats of navigation. Each one has to be aimed precisely, threading the spacecraft past the planet at the right altitude, the right angle, and the right speed. A small error in the targeting could send Parker into the wrong orbit, missing the sun by millions of miles, or worse, slamming the spacecraft into Venus itself. The mission designers calculated the trajectory years in advance, with each Venus encounter shrinking Parker's perihelion, the closest point of its orbit to the sun, by a fixed amount. The first close approach was at 15 million miles. The next was at 15 million miles again, then 12, then 12, then 9, then 9, and so on until the final approach distance of 3.8 million miles was reached in December 2024. Each Venus flyby also gave the science team an opportunity to study Venus itself. Parker's instruments, originally designed for solar observations, recorded data about Venus's atmosphere, its magnetic environment, and even its night-side surface. The WISPR camera, designed to image the faint solar corona, turned out to be sensitive enough to see thermal radiation from Venus's hot surface through gaps in the cloud cover. Those images showed surface features that had only previously been mapped by radar. It was an unexpected bonus, science from a planet that was not even a target of the mission. By December 2024, after 6 years of flight and 21 orbits, Parker was ready for its closest approach. The spacecraft would pass within 3.8 million miles of the solar surface, traveling at 430,000 miles per hour relative to the sun. For comparison, that speed would take you from New York to Los Angeles in about 20 seconds. It is the fastest any human-made object has ever moved. During that closest approach, Parker would be inside the corona, below the Alfvén critical surface, in the region where the solar wind is born. The spacecraft would be operating autonomously, out of contact with Earth, surrounded by plasma at over 2 million degrees Fahrenheit, with only its heat shield between it and destruction. The engineers who built it could only wait. The spacecraft would either come out the other side with its data intact, or it would not. There was no way to intervene if something went wrong. The shield had to work. And against every expectation of how fragile such a machine should be in such an environment, it did. The first major discovery of the Parker Solar Probe mission was the one that nobody had predicted, the one that solar physicists are still arguing about years later. The switchbacks. Those violent reversals in the magnetic field that the spacecraft detected on its very first close approach in 2018 turned out to be far more common, far more energetic, and far more important than anyone initially realized. As Parker made subsequent close passes, the picture grew clearer. The switchbacks were not occasional anomalies. They were a fundamental feature of the inner solar wind, present in vast numbers throughout the regions Parker was sampling. The scale of the phenomenon took the science team by surprise. During some close approaches, Parker would encounter hundreds of switchbacks in a single pass through the corona. They came in clusters, sometimes lasting hours, sometimes punctuated by quieter periods of more orderly magnetic field behavior. They had a characteristic shape, an S-curve in the field lines, with the magnetic vector flipping through a wide angle and then returning to its original orientation. The flips could be partial, with the field rotating only 30 or 40 degrees, or they could be complete, with the field pointing almost exactly opposite to its starting direction. The largest switchbacks were so dramatic that they momentarily reversed the entire local magnetic environment of the spacecraft. What made the switchbacks scientifically explosive was not just their existence, but what they implied. Each switchback carried significant energy. The magnetic field is one of the main carriers of energy in the solar wind, and a region where the field is bent into a violent S-curve has more energy stored in it than a region where the field is smooth. When Parker measured the total energy contained in the switchbacks across all its close approaches, the number was enormous. The switchbacks collectively carried enough energy to account for a substantial fraction of the energy needed to heat the corona and accelerate the solar wind. They were not just curiosities. They might be a fundamental piece of the puzzle that solar physicists had been trying to solve for 70 years. This is where the immediate scientific reaction became intense. If the switchbacks were carrying energy outward from near the sun, the obvious next question was where that energy was coming from. What process at or near the solar surface was generating these violent, energetic structures and sending them streaming out through the corona? The answer would tell scientists something fundamental about how the sun transfers energy from its interior to its atmosphere and ultimately to the solar wind that fills the entire heliosphere. Two main theories emerged from the early analysis. The first theory tied the switchbacks directly to the solar surface. According to this view, the switchbacks form when magnetic field lines near the surface get twisted and tangled by the constant churning of the convection zone. The plasma beneath the photosphere is in constant motion, like water boiling in a pot, and that motion drags the magnetic field lines around with it. Occasionally, the twisting becomes so severe that the field lines snap and reconnect in new configurations, releasing a sudden burst of energy. That burst would send a magnetic disturbance propagating outward through the corona, and by the time it reached Parker, it would appear as a switchback. This theory had the advantage of connecting the switchbacks to a known physical process. Magnetic reconnection on small scales had been proposed as a coronal heating mechanism for decades, the nanoflare hypothesis described earlier. If the switchbacks were the visible signature of nanoflares carrying energy outward, then Parker might have finally caught the corona being heated. The data would be the long-awaited smoking gun for one of the two main theories of coronal heating. The second theory placed the origin of the switchbacks higher up. According to this view, the switchbacks form in the corona itself, not at the surface, through interactions between different streams of solar wind moving at different speeds. When a slower stream is overtaken by a faster one, or when streams flowing along different magnetic field lines come into contact, the resulting turbulence could generate switchback-like structures. This theory had the advantage of being able to produce switchbacks continuously without requiring discrete events at the surface. The disadvantage was that it did not explain why the switchbacks had such a distinctive S-shape, or why they came in clusters with characteristic energies. For several years, the two theories competed without a clear winner. Then, in 2023, a team analyzing data from Parker's eighth close approach published a paper that shifted the balance. They had found a correlation between the switchbacks and specific features on the sun's surface. Looking back at imagery from the Solar Dynamics Observatory taken during the time Parker was sampling switchback clusters, the team identified small magnetic loops at the boundaries of coronal holes, the regions where the fast solar wind originates. These loops appear to be sites of ongoing reconnection, and their locations corresponded to the regions where Parker was detecting the largest concentrations of switchbacks. The findings suggested that interchange reconnection, the process where open magnetic field lines reconnect with closed loops near the surface, was generating the switchbacks. As an open field line meets a closed loop, the field lines exchange configurations. The previously open line becomes a small closed loop, and the previously closed loop becomes a new open line, but with a sharp bend or kink in it from the reconnection geometry. That kink then propagates outward along the field, eventually appearing as a switchback when Parker flies through it. This explanation accounted for many features of the observations. It explained why switchbacks came in clusters, because reconnection events at the boundaries of coronal holes tend to occur in groups. It explained the characteristic S-shape, because the reconnection geometry naturally produces sharp bends in the field lines. It explained why the switchbacks carried so much energy, because reconnection is one of the most efficient ways nature has of converting magnetic energy into kinetic energy. And it tied the switchbacks to the source of the fast solar wind, suggesting that the same process that creates the switchbacks might also be responsible for accelerating the wind itself. But not every solar physicist was convinced. Other research groups continued to argue that the switchbacks formed higher up in the corona through turbulent interactions in the solar wind. They pointed to features of the data that the interchange reconnection model did not fully explain. The size distribution of switchbacks did not quite match what the model predicted. The frequency of switchbacks at different distances from the Sun did not behave the way the model required. The debate continues to this day, with new data from each Parker pass adding more evidence on both sides. What is not in dispute is that the switchbacks have fundamentally changed how solar physicists think about the connection between the Sun and the solar wind. Before Parker, the standard picture had the wind flowing more or less smoothly outward, with turbulence as a small perturbation on top of a fundamentally orderly flow. After Parker, that picture is no longer tenable. The inner solar wind is violent, structured, full of energetic events on small scales. The smooth, gentle outflow envisioned by the original models is replaced by a chaotic, turbulent environment shaped by countless magnetic disturbances of varying sizes and energies. There was another aspect of the switchback discovery that took the scientific community some time to fully appreciate. The same kind of structures had been seen before, but in very different contexts. Decades earlier, the Ulysses spacecraft, which had flown over the Sun's poles in the 1990s, had recorded occasional magnetic field reversals in the solar wind at high latitudes. Those reversals had been treated as oddities, isolated events that probably did not represent anything fundamental. Now, with Parker showing that such reversals were ubiquitous near the Sun, the old Ulysses data could be reinterpreted. The reversals had not been anomalies. They had been the surviving remnants of switchbacks generated near the Sun and carried outward by the wind, gradually dissipating, but still detectable hundreds of millions of miles away. That realization had implications beyond just solar physics. If switchbacks are a fundamental feature of how stars connect to their stellar winds, then every star in the universe might be generating similar structures. The mechanism Parker uncovered near our Sun might be at work near every star, shaping the stellar winds that flow throughout every galaxy. A discovery made 3.8 million miles from our own Sun might turn out to be a fundamental feature of how stars in general behave. That kind of generalization, from one star to all stars, is exactly the kind of leap that solar physics had been hoping Parker would enable. But the switchbacks were only the first of Parker's major revelations. As the spacecraft made more close approaches, it found things that were even harder to explain. The second major discovery came from a region nobody had ever measured directly. As Parker Solar Probe made its progressively closer approaches through 2020 and 2021, the spacecraft began crossing a boundary that until then had only existed in textbooks and theoretical models: the Alfvén critical surface. This is the invisible line that marks the true edge of the Sun's atmosphere, the place where the solar wind finally breaks free of the magnetic grip of its parent star. Below it, the corona and the Sun are still magnetically connected. Plasma can flow back and forth. Disturbances can propagate in either direction. Above it, the solar wind is gone for good, racing outward at speeds that exceed the speed at which magnetic disturbances can travel back to the Sun. In April 2021, during Parker's 8th close approach, the spacecraft passed through this boundary for the first time. The data took months to analyze and verify, but by December of that year, NASA was ready to make the announcement official. Parker had touched the Sun. For the first time in history, a human-made object had entered the atmosphere of a star. The spacecraft had spent about 5 hours inside the Alfvén critical surface, sampling plasma that was still gravitationally and magnetically bound to the Sun, plasma that scientists had only ever observed from the outside looking in. What Parker found inside that boundary was the second major surprise of the mission. The Alfvén critical surface was not where the models said it would be. It was also not the shape the models had predicted. Theoretical work going back decades had assumed the boundary would be roughly spherical, perhaps slightly distorted by the sun's rotation, but generally a smooth surface at a fairly consistent distance from the sun. Parker's data showed something very different. The boundary was uneven, with significant dips and bulges. In some places, it extended outward to about 20 solar radii from the surface. In other places, it dipped inward to 15 solar radii or less. The variation was not random. It correlated with magnetic structures in the corona, with the boundary pulled inward over regions of strong magnetic activity and pushed outward over quieter regions. This had implications that took some time to fully appreciate. If the Alfvén critical surface is wrinkled and dynamic rather than smooth and stable, then the process by which the solar wind breaks free of the sun is more complex than scientists had assumed. The solar wind does not just smoothly accelerate outward and cross a clean boundary into interplanetary space. Different parcels of plasma cross at different distances, at different times, depending on the local magnetic environment. Some plasma might cross the boundary, then get pushed back inside it by a passing magnetic disturbance, then cross again later. The transition from bound solar atmosphere to free-flowing solar wind is not a single moment, but a messy, ongoing negotiation between the plasma and the magnetic field. The second discovery also brought new clarity to where the solar wind actually originates. For decades, scientists had known the wind came from the sun, but the precise locations where it emerged from the surface had been difficult to pin down. The fast solar wind was clearly associated with coronal holes, those dark regions visible in ultraviolet images where the magnetic field lines extend openly outward instead of looping back to the surface. But the slow solar wind, which makes up much of the wind that reaches Earth, had no clear surface source. Different theories pointed to different possible origins. Some scientists thought it came from the edges of coronal holes. Others believed it came from streamers, the bright magnetic structures that extend outward from the sun's equator during quiet times. Still others suggested it originated from small, dynamic regions called pseudo-streamers, where the magnetic geometry was particularly complex. Parker's data, particularly from inside the Alfvén critical surface, helped resolve this question, though not entirely. The spacecraft found that the slow solar wind near the sun was not coming from a single type of source. It was emerging from a variety of regions, with different parts of the wind originating from different surface features. Some streams traced back to the edges of coronal holes. Some came from the bases of streamers. Some appeared to come from regions where the magnetic field was undergoing the same kind of interchange reconnection that was producing the switchbacks. The slow solar wind, it turned out, was not a single phenomenon with a single source. It was a composite made up of multiple streams that mixed and merged as they flowed outward. This finding had a particular consequence that excited mission planners and worried satellite operators in equal measure. If the slow solar wind has multiple sources, and if its properties depend on which source it comes from, then accurately predicting space weather becomes far more complicated than previously assumed. Space weather forecasting depends on knowing what the solar wind will do when it arrives at Earth. Solar storms can damage satellites, disrupt radio communications, knock out power grids, and force aircraft on polar routes to be rerouted. The better we can predict the wind, the better we can protect the technology we depend on. But if the wind's properties depend on small-scale features near the sun that we cannot observe directly from Earth, then prediction becomes much harder. We need to know not just whether a storm is coming, but what kind of storm it is, what its magnetic configuration will be, how it will interact with Earth's own magnetic field. Parker's findings suggest that the answers depend on processes happening too close to the sun to be observed by any spacecraft other than Parker itself. There was a third aspect of the discovery that proved scientifically important. Parker found that the magnetic field structure inside the Alfvén critical surface was full of small-scale structures that the models had not predicted. Tiny magnetic loops. compact regions of plasma with distinct properties. Localized patches where the field strength varied sharply over small distances. These structures suggested that the corona was far more textured than the smooth, large-scale models had assumed. The whole region near the Sun was, in effect, a turbulent, dynamic environment, with small-scale features playing as important a role as the large-scale structures that had been the focus of decades of remote observation. Some of these small-scale structures behaved in ways that surprised even the most experienced solar physicists. There were regions where the plasma density was unexpectedly low, almost as if pockets of near vacuum existed within the otherwise dense coronal material. There were regions where the magnetic field strength dropped sharply over a few hundred miles, then recovered. There were boundaries where adjacent parcels of plasma had completely different properties, despite being right next to each other, with apparently nothing keeping them separate. These findings led to a growing suspicion that the corona was not just turbulent in a statistical sense, but actively structured by processes that scientists had not previously appreciated. There was also a subtle but important finding about how the plasma in the corona was heated. Parker carried instruments that could measure not just the bulk temperature of the plasma, but the temperatures of individual particle species, protons, electrons, and heavy ions like helium and oxygen. In the regions Parker sampled, these species were not all at the same temperature. The heavy ions were significantly hotter than the protons. The protons were significantly hotter than the electrons. The temperature differences were larger than the standard models had predicted, and they suggested that whatever was heating the corona was preferentially heating certain species over others. This selective heating is a signature of specific kinds of plasma waves. Ion cyclotron waves, for example, can heat heavy ions much more efficiently than electrons. The fact that Parker was seeing exactly the kind of temperature differences these waves would produce was strong evidence that wave heating, the first of the two main theories described earlier, was at work in the corona. But it was not the only mechanism. The data was also consistent, with some contribution from nanoflares and reconnection events. The picture that emerged was one of multiple processes operating simultaneously, with waves and reconnection both contributing to the energy budget of the corona, possibly in different regions or at different times. This was the second discovery, not a single revelation, but a layered, complex finding. The boundary of the Sun's atmosphere was uneven and dynamic. The slow solar wind had multiple sources. The corona was textured at small scales in ways the models had not anticipated. And the heating was being done by a combination of processes, not just one. Each piece of the puzzle was a partial answer to a question scientists had been asking for decades. Each piece also raised new questions, and Parker was only halfway through its planned mission. The third major discovery would come from a direction nobody expected. Not from the magnetic field, not from the solar wind, but from the dust. The third major discovery began as a footnote and grew into something much stranger. When Parker Solar Probe was being designed, the science team paid careful attention to the threat posed by dust. The space between the Sun and Earth is filled with microscopic particles, the slow accumulation of comet debris and asteroid fragments built up over billions of years. Most of these particles are smaller than a grain of sand. Many are smaller than a particle of smoke. From a distance, they are invisible. But to a spacecraft moving at 430,000 miles per hour, even a particle weighing a billionth of a gram becomes a hypervelocity projectile capable of punching through metal. The mission designers had calculated the dust environment carefully. Models built from decades of observation predicted that the dust would get denser as Parker approached the Sun, peaking somewhere in the inner solar system before falling off as particles vaporized in the heat. The spacecraft was built to withstand impacts from this expected dust population. The heat shield, in particular, was designed to absorb hits without being compromised. The instruments were shielded as much as possible. The trajectory was planned to minimize exposure during the most dangerous portions of each orbit. The team expected damage. They accepted it as a cost of doing science in such an extreme environment. What they did not expect was that the dust would behave so differently from the models. The first hints came from Parker's third close approach in 2019. The WISPR camera, designed to image the corona and the solar wind, began returning pictures of something the science team had not anticipated. A long, faint streak of light extending behind Mercury, the innermost planet of the solar system. The streak was thin, diffuse, and aligned with the planet's orbital trajectory. It looked like a comet's tail, but Mercury is not a comet. Mercury is a small, airless world with no obvious mechanism for producing such a feature. And yet the streak was there, clearly visible in Parker's images, extending for millions of miles behind the planet. The science team eventually identified the feature as a dust tail, made of microscopic particles being stripped from Mercury's surface by the solar wind and the constant bombardment of micrometeoroids. The planet, it turned out, was leaving a faint trail of its own dust behind it as it orbited the sun. The trail had never been observed before, partly because no spacecraft had ever been in a position to see it, and partly because no one had specifically looked for it. Parker, in the right place at the right time, with the right instrument, had discovered an entirely new feature of the inner solar system. The Mercury dust tail was just the beginning. As Parker made more close passes, the WISPR camera continued to record images of the dust environment around the sun, and the patterns that emerged grew increasingly unexpected. There were structures in the dust that the models had not predicted: filaments, bands, regions where the dust appeared to be organized into clumps or streams. Some of these features could be traced back to specific comets, the debris trails left behind as comets passed through the inner solar system in the distant past. Others had no obvious source. They were just there, faint streaks and shadows in the dust, the relics of processes that had shaped the inner solar system in ways scientists had not previously documented. But the most surprising finding about the dust was something the team had glimpsed on the very first close approach and only fully understood after years of additional data: the dust-free zone. As Parker approached the sun, the dust did not get denser as the models had predicted. It got thinner, not just slightly thinner, dramatically thinner. The density of microscopic particles dropped off sharply at a distance of about 5 million miles from the sun, and inside that distance, the dust environment was essentially empty. A clear, swept zone where the particles that filled the rest of the inner solar system simply were not there. The existence of such a zone had been theorized as far back as the 1970s. The reasoning was straightforward. Close to the sun, the intense heat would vaporize small particles, turning them from solid grains into gas. The radiation pressure from sunlight would push the smallest particles outward, even against the sun's gravity. The combination of vaporization and radiation pressure should produce a clear region near the sun where dust could not survive. The theoretical prediction had existed for half a century, but until Parker, no one had ever directly observed it. What Parker found confirmed the prediction in its basic outline, but raised new questions about the details. The boundary of the dust-free zone was sharper than expected. The transition from a dust-filled region to a nearly empty one happened over a relatively narrow range of distances, rather than gradually as some models had suggested. The exact distance at which the zone began varied from one close approach to another, suggesting that the boundary was dynamic, responding to changes in solar activity and the structure of the solar wind. And inside the zone, while the dust was largely absent, it was not completely gone. Parker still occasionally detected impacts from small particles, suggesting that some material could survive even very close to the sun, perhaps the larger, more robust grains that took longer to vaporize. The discovery of the dust-free zone has practical implications for future missions. If a spacecraft can be designed to survive the thermal environment near the sun, the dust environment, at least, will not be a major threat in the innermost regions. The hardest part of operating near the sun, in terms of micrometeoroid damage, is actually further out, where the dust density is highest. Once a spacecraft passes into the dust-free zone, it is in cleaner space than at almost any other location in the inner solar system. This insight has been incorporated into the planning for follow-on missions, including proposed concepts that would take spacecraft even closer to the Sun than Parker has gone. But the dust environment also produced one of the strangest single events of the mission. In 2021, during one of Parker's close approaches, the spacecraft passed through a particularly dense cloud of dust that had not been predicted by any model. The encounter lasted only minutes, but during that brief period, the spacecraft was hit by thousands of dust impacts in rapid succession. The hits were detected by sensors mounted on the spacecraft body, which can measure the tiny electrical discharges produced when a hypervelocity particle strikes the surface. The density of the impacts was so high that, for a few minutes, the spacecraft was essentially being sandblasted by microscopic debris. The most likely explanation involved a comet. Comet Atlas, formerly known as C2019Y4, had broken apart in early 2020 as it approached the Sun. The fragments had spread out along the original comet's orbit, creating a stream of debris that intersected Parker's path. The spacecraft had flown straight through the heart of a fresh debris field, and the dust impacts were the result. The encounter was a stroke of incredibly bad luck and incredibly good science. No previous spacecraft had ever directly sampled the dust trail of a recently disintegrated comet so close to the Sun. The data Parker collected during those few minutes gave researchers an unprecedented look at the composition and dynamics of cometary debris in the inner solar system. The dust discoveries collectively painted a picture of the inner solar system that was far more dynamic and structured than scientists had previously appreciated. The Mercury dust tail showed that even airless worlds could be losing material to space. The dust-free zone confirmed a long-standing prediction while raising new questions about its boundaries and behavior. The comet debris encounter demonstrated that the dust environment near the Sun was constantly being refreshed by events happening throughout the solar system. The dust, it turned out, was not just a hazard to be avoided. It was a science target in its own right, a window into processes that had been shaping the inner solar system for billions of years. There was one more aspect of the dust environment that turned out to have unexpected scientific value. The same dust impacts that posed a hazard to the spacecraft also turned out to be useful. When a high-velocity particle strikes a spacecraft, the impact vaporizes both the particle and a tiny portion of the surface, producing a brief flash of plasma. Parker's Field's instrument was sensitive enough to detect these plasma flashes, and the science team realized they could be used to study the dust population in real time. Each impact carried information about the size, velocity, and composition of the particle that produced it. Over thousands of impacts across multiple close approaches, the team built up a detailed map of the dust environment near the Sun, including regions and properties that had never been characterized before. The discoveries kept coming. Each close approach added new layers to the picture, new features to the inner solar system that had never been seen before. And by 2023, Parker had begun finding something that was harder to fit into any existing framework. The fourth major discovery is the one that scientists have the most trouble explaining. It involves a set of measurements Parker made during its closer approaches, particularly those after 2022, when the spacecraft began regularly passing inside the Alfvén critical surface. The measurements concern the temperature of the plasma in the corona, and they do not match what the laws of physics, as currently understood, predict they should be. The basic problem is this: plasma cools as it expands. This is one of the most fundamental rules in physics, derived from the conservation of energy and the behavior of gases. When a parcel of gas expands into a larger volume, the energy of its particles is spread over a wider region, and the temperature drops. The relationship is well defined mathematically. For an adiabatic expansion, where no heat is added or removed from the parcel, the temperature drop is determined by the change in volume according to a precise formula. This rule applies to gases in laboratory experiments, to the atmospheres of planets, to the interiors of stars, and to the plasma that fills the space between worlds. The solar wind is a plasma that is expanding continuously. As it flows outward from the Sun, the wind spreads into an ever larger volume, and according to adiabatic cooling, it should cool down. The exact rate of cooling depends on the geometry of the expansion and the composition of the plasma, but the basic prediction is unambiguous. Far from the sun, the solar wind should be much colder than it is near the source. By the time it reaches Earth, the temperature should have dropped to a small fraction of what it was in the corona. When scientists measured the temperature of the solar wind at Earth's orbit, decades before Parker launched, they found something that did not match the prediction. The wind was hotter than it should have been. Not catastrophically hotter, but consistently warmer than pure adiabatic cooling would produce. The discrepancy was small but persistent, and it pointed to some heating mechanism operating in the wind as it traveled outward. Something was depositing energy into the plasma along the way, slowing the cooling and keeping the wind warmer than basic physics would predict. For decades, scientists assumed the explanation involved turbulence. The solar wind is turbulent on small scales, full of waves and eddies and density fluctuations. Turbulence, when it dissipates, deposits heat into the plasma. The standard picture had turbulence generated near the sun being gradually dissipated as the wind flowed outward, providing the heating needed to explain the higher-than-expected temperatures at Earth. This was a plausible explanation, but it had never been directly tested. To test it, you would need to measure the wind close to the sun, where the turbulence is strongest, and then measure it at greater distances, watching how the turbulence and the temperature evolved as the plasma flowed outward. Parker was supposed to do exactly that, and what Parker found has unsettled the standard picture in ways that are still being worked out. In the regions Parker sampled, particularly inside the Alfvén critical surface, the temperature of the plasma was higher than expected, significantly higher. The protons in the wind, the dominant species, were hotter than the basic models predicted by factors of 2 or 3 in some regions. The heavy ions were even hotter. Most strikingly, the temperatures did not always decrease with distance from the sun in the way they should. In some regions, the plasma actually appeared to be reheating as it moved outward, briefly increasing in temperature before resuming its overall decline. This was not supposed to happen. The reheating was small, often just a few % change in temperature over a few 100,000 miles of travel, but it was there in the data, repeatedly, across multiple close approaches and multiple instruments. The plasma was somehow gaining energy as it flowed outward through regions where, according to the standard picture, no significant heating source should exist. The science team approached the problem cautiously. Anomalous results in solar physics have a long history of turning out to be instrument artifacts or calibration errors. The team checked everything. They cross-validated measurements from different instruments. They compared data from different close approaches. They ran computer models to see if any known physical process could produce the patterns they were seeing. After more than a year of analysis, they concluded that the reheating was real. It was not an instrument error. The plasma was being heated in regions where the existing models predicted no heating should occur. What could be producing the heating? The leading candidates involved various forms of wave-particle interaction. Plasma waves can carry energy from one region to another, depositing that energy as heat when they dissipate. If waves were being generated near the sun and propagating outward into the regions Parker was sampling, they could provide the heating source. But this raised its own problems. The waves would have to be of specific types and amplitudes to produce the patterns observed. They would have to dissipate at the right distances to explain the reheating. And the energy budget had to work out, with enough total wave energy available to account for the heating scene. A more radical possibility was that the reheating was being produced by switchbacks. The S-shaped magnetic field reversals that Parker had discovered carried significant amounts of energy, as discussed earlier. If switchbacks were dissipating as they flowed outward, depositing their energy into the surrounding plasma, they could provide the heating mechanism that the data required. This would tie together two of Parker's major discoveries, linking the switchbacks not just to the source of the solar wind, but to its ongoing heating throughout the inner heliosphere. It would also raise new questions about what process was generating the switchbacks at the source. since the energy ultimately had to come from somewhere. There is another aspect of the temperature measurements that has been even harder to explain. Parker found that different particle species in the same parcel of plasma were heated to different temperatures, and that the temperature differences depended on the species in ways that did not always match theoretical predictions. The protons were hot. The electrons were colder than the protons. The heavy ions were hotter than both, sometimes by factors of 10 or more, with the heaviest ions being the hottest. This kind of preferential heating of heavy species is a signature of certain types of plasma waves, particularly ion cyclotron waves. The existence of preferential heating was not in itself a surprise. It had been predicted by theory. What was surprising was the magnitude. The temperature differences between species were larger than the standard wave heating theories could comfortably explain. Some heavy ion temperatures were so high that they pushed the limits of what any known heating mechanism could produce. The plasma was hotter than the theory said it should be, in ways the theory had not anticipated. And the patterns of heating, with different species heated to different degrees in different regions, suggested that multiple mechanisms might be operating simultaneously, each affecting different species in different ways. The science team has been working through these problems for several years, and the picture remains incomplete. There is no single answer to the question of how the corona and inner solar wind are heated. There is no consensus on the relative importance of waves versus reconnection versus switchback dissipation. There is no settled explanation for why heavy ions are so much hotter than other species, or why the heating varies so dramatically from one region to another. What Parker has done is provided the data that any future explanation will have to account for. The data is real. The patterns are clear. The theoretical work is still catching up. This is what some have referred to when they say Parker has recorded measurements NASA refuses to fully explain. The agency is not hiding anything. The data is public, available to researchers around the world. But when asked what the data means, NASA scientists, like scientists everywhere, are careful. They say the data is consistent with multiple possible explanations. They say further analysis is needed. They say the mechanisms remain unclear. This is not evasion. It is the honest acknowledgement that the data has outrun the theory, and the theory needs time to catch up. There is one more aspect of the heating problem that adds an additional layer of mystery. Parker has detected occasional bursts of intense heating that do not appear to be associated with any obvious surface source. The bursts are brief, lasting from seconds to minutes. They produce sudden spikes in plasma temperature that quickly subside. They occur seemingly at random throughout the regions Parker has sampled, and no one knows what causes them. The heating bursts are real. They are detected by multiple independent instruments. They produce signatures that cannot easily be explained as instrument errors, but their origin is currently unknown. Whatever process is producing them operates on time scales too short and length scales too small for any other spacecraft or telescope to observe. Parker is the only instrument that can detect them, and Parker can only sample them briefly as it flies past. The data is tantalizing but incomplete. These are the kinds of measurements that keep solar physicists awake at night. The plasma is hotter than it should be. The heating mechanisms are not fully understood. The bursts of intense heating have no clear source. The corona is doing things that the textbooks said were not supposed to be possible. And Parker is the only spacecraft that has ever been close enough to see them. The mid-mission climax came on December 24, 2024, Christmas Eve. While most of the world was preparing for the holiday, a small team of engineers and scientists at the Johns Hopkins Applied Physics Laboratory in Maryland sat in front of their consoles, waiting. Parker Solar Probe was about to make its closest approach yet, 3.8 million miles from the Sun's surface. Traveling at 430,000 miles per hour, the fastest, closest passage of a star ever attempted by humanity. There was no way to know in real time whether the spacecraft survived. The communication delay between Earth and Parker during the encounter was significant, and during the closest approach itself, the spacecraft was completely out of contact. The heat shield was pointed toward the Sun, which meant the antenna was pointed away from Earth. For about a week around closest approach, Parker would be operating entirely on its own. executing pre-programmed commands, taking measurements, and storing the data on internal recorders for transmission later. The team would not know if the spacecraft had survived until 2 days after closest approach, when Parker rotated to point its antenna back toward Earth and sent a single, simple signal, a beacon tone, a confirmation that the spacecraft was still alive. On December 26th, the beacon arrived. Parker had survived. The data would take weeks to fully downlink, but the spacecraft was intact, functioning, and ready to continue its mission. The engineers cheered, some cried. Many of them had spent their entire careers on this mission, some going back to the original Solar Probe Plus concept of the early 2000s. The success of the closest approach was the culmination of decades of work, but the science was what mattered most. What had Parker recorded down there, inside the corona, closer to the sun than anything humanity had ever sent? The first analyses began arriving in early 2025, and what they revealed has reframed how solar physicists think about the inner regions of our star. The first major finding from the closest approach concerned the magnetic field. Throughout the close approach, Parker recorded magnetic field strengths and configurations that had never been measured before. The field was stronger than expected in some regions, weaker in others, and the patterns of variation suggested that the small-scale structure of the corona was even more complex than the earlier close approaches had indicated. Parker recorded magnetic field events lasting just fractions of a second, brief flickers in the field that the slower instruments on previous missions could not have resolved. The corona, at the smallest scales Parker could probe, was alive with activity. Among these small-scale events were structures that the science team initially struggled to classify. They were not switchbacks, exactly, though they shared some features with them. They were not standard magnetic loops or flux tubes, though they had elements of those structures too. They appeared to be a new kind of magnetic feature, smaller than anything previously catalogued, lasting only briefly before dispersing into the background plasma. The team has tentatively called them coronal eddies, a placeholder name while their nature is still being determined. They may turn out to be the building blocks of larger phenomena, the fundamental units from which switchbacks and other structures are assembled. Or they may be a completely new category of magnetic activity in stellar atmospheres, something that exists only in the inner corona and has never been observed elsewhere. The closest approach also produced the clearest evidence yet of the heating bursts that had been detected on earlier passes. During the deepest part of the encounter, Parker recorded several intense, localized spikes in plasma temperature, each lasting only seconds, each producing a sudden flash of heating in the surrounding plasma. The bursts were more numerous and more energetic than those seen at greater distances. They appeared to be a phenomenon specific to the deepest corona, the region just above the sun's surface where the heating problem is at its most acute. Whatever process is driving these bursts, it is most active in exactly the region where the corona is being heated. But the most striking finding from the closest approach concerned something the science team had not specifically been looking for. As Parker passed through the corona, the WISPR camera continued to take images, and in those images, the team identified something unusual, a region of the corona that appeared to be structured in ways that did not match any of the standard models. The region showed evidence of being threaded by extremely fine magnetic structures, much finer than the resolution of any previous observations. The structures were arranged in patterns that suggested coherent organization across distances of millions of miles, despite their individual sizes being only thousands of miles or less. This finding, when fully analyzed, has implications that reach beyond solar physics. The patterns the team observed are consistent with a phenomenon called magnetic carpet dynamics, the constant emergence, evolution, and disappearance of small magnetic features at the sun's surface. The carpet had been theorized and observed in low resolution by previous spacecraft, but Parker's data revealed it in unprecedented detail. The magnetic carpet, it turned out, was not just a feature of the sun's surface. It extended upward into the corona, organizing the plasma on scales that connected the smallest features to the largest. The corona was, in effect, woven together by the carpet, with magnetic threads of all sizes, interlocking into a single dynamic system. This insight changes how solar physicists think about the connection between the sun and its atmosphere. The traditional view had separated the photosphere, the chromosphere, and the corona into distinct layers, each with its own dominant physical processes. Parker's data suggests that these layers are far more interconnected than the layered model implies. Magnetic structures at the surface have direct consequences in the upper corona. Plasma flows in the corona influence the behavior of the surface. The entire system, from the surface up through the corona and out into the solar wind, behaves as a single integrated whole, with information and energy flowing in both directions on time scales much faster than previously appreciated. There is one more finding from the closest approach that deserves attention. During the encounter, Parker recorded data that suggested the existence of localized regions in the corona where the standard fluid description of plasma behavior breaks down. Most plasma physics is based on treating the plasma as a fluid, with bulk properties like density, temperature, and velocity that vary smoothly from one location to another. This description works well in most circumstances. But in some regions Parker sampled, the plasma appeared to be behaving in ways that the fluid description could not capture. Individual particles were moving in coordinated patterns that suggested kinetic effects, where the discrete nature of individual particles becomes important, dominating the dynamics in ways that bulk descriptions cannot predict. Kinetic plasma physics is well developed mathematically, but it is much harder to apply to real systems than fluid descriptions. Most models of the corona use fluid approximations because the full kinetic equations are computationally expensive and analytically intractable. If significant regions of the corona require full kinetic treatment, then much of the existing modeling work needs to be revisited. The corona might be a kinetic system, not a fluid one, in ways that have profound implications for how scientists approach the heating and acceleration problems. The closest approach data is still being analyzed more than a year after the encounter took place. New findings continue to emerge from the same set of measurements as different research groups apply different analytical techniques. The full implications will take years to work out, but the basic picture is clear. Parker, at its closest to the sun, recorded a region of plasma that is more complex, more dynamic, more heated, and more structured than anyone had predicted. The closest approach did not provide simple answers. It revealed new layers of mystery, new questions to investigate, new phenomena that the existing theories cannot fully explain. This is the climax of the Parker Solar Probe story so far. Not a single shocking discovery, but a layered, accumulating realization that the sun is doing things at its boundaries and in its atmosphere that humanity is only beginning to understand. The spacecraft will continue making close approaches through 2026 and beyond, gathering more data, sampling more regions, building a more complete picture of the inner sun. But what it has already found is enough to fundamentally change the field of solar physics. The corona is not a smooth, gently flowing atmosphere being heated by some single, dominant mechanism. It is a chaotic, structured, multi-scale environment shaped by countless interacting processes, with switchbacks and reconnection events and turbulence and waves and kinetic effects all playing roles, all interacting in ways that the existing models cannot yet capture. The sun, the most studied object in astronomy, has turned out to be doing things that no one expected, and we are only just beginning to figure out what they mean. The discoveries Parker Solar Probe has made are not just additions to a textbook. They are forcing a fundamental rewrite of how scientists understand stars. For decades, solar physics had built itself around a particular framework. The sun was treated as a relatively well-understood system, with the major puzzles confined to a few specific areas like the coronal heating problem and the solar wind acceleration mystery. Most of the field's effort went into refining the details of an existing picture, not questioning the picture itself. Parker has changed that. The data the spacecraft has returned does not just refine the existing models. In many places, it contradicts them. And the contradictions are not minor. The most direct casualty has been the simple, layered model of the sun's atmosphere. For generations, Students of solar physics have learned about the Sun as a series of distinct regions stacked one on top of the other. The core, where fusion happens; the radiative zone, where energy slowly migrates outward; the convection zone, where plasma churns; the photosphere, the visible surface; the chromosphere, the thin layer above; the corona, the outer atmosphere. Each layer had its own properties, its own dominant physics, its own characteristic behaviors. The picture was tidy. It was easy to teach. It was easy to remember. That picture is no longer accurate, or at least no longer complete. Parker has shown that the corona is connected to the surface in ways the layered model could not capture. Small magnetic structures at the photosphere have direct consequences in the corona millions of miles above. The boundary between the chromosphere and the corona, traditionally drawn as a sharp transition, turns out to be fuzzy and dynamic, with material flowing back and forth across it in ways that the standard picture did not predict. The corona itself, far from being a uniform region, is full of structures and processes that vary on scales from thousands of miles down to the kinetic limits where individual particles dominate. The clean layers of the textbook diagram have given way to a far more interconnected, dynamic, multi-scale system. This has consequences beyond just how scientists describe the Sun. It has consequences for how they model stars in general. The Sun is not just one star. It is the star, the example used to develop and test theories of stellar atmospheres, stellar winds, stellar magnetism. What scientists learn about the Sun gets applied to every other star in the universe. If the Sun's atmosphere is more complex than previously thought, then so are the atmospheres of all the other stars. The picture changes everywhere at once. The coronal heating problem, the 70-year mystery that drove the development of Parker in the first place, has not been definitively solved, but it has been transformed. Before Parker, the debate was largely between two main theories: wave heating versus nanoflares. Each side had its supporters, its evidence, its preferred set of observations. The community was divided. Parker's data has not produced a single winner in that debate. What it has produced is a growing consensus that both mechanisms are at work, along with several others that had previously been considered less important: switchback dissipation, interchange reconnection, kinetic effects in particular regions. The corona is being heated by a combination of processes, not a single dominant one. The question is no longer which mechanism is correct, but how the different mechanisms combine, in what proportions, in what regions, under what conditions. This is a more complicated answer than scientists had hoped for. It is also more honest. Nature does not always cooperate with our desire for clean, simple explanations. The corona, it turns out, is not heated by one elegant process that physicists can write on a chalkboard. It is heated by a noisy, messy, multi-scale system in which many different processes interact and contribute. Building a complete theory of coronal heating will require modeling all of these processes simultaneously in ways that are computationally demanding and conceptually challenging. The community is still working out how to do that. The solar wind acceleration problem has been similarly transformed. Before Parker, scientists knew the wind was being accelerated somehow, but the details were unclear. The leading theories involved pressure gradients in the corona, wave-driven momentum transfer, and various combinations of magnetic effects. Parker's discoveries about switchbacks have added a new dimension to this question. If switchbacks are carrying significant amounts of energy and momentum outward from the Sun, they may be playing a role in accelerating the wind itself. The wind, in this picture, is not just being pushed outward by a smooth pressure gradient. It is being given repeated kicks by countless small magnetic events, each contributing a bit of energy and momentum, the cumulative effect being to accelerate the plasma to its observed speeds. This picture has implications for understanding stellar winds throughout the universe. Stars lose mass through their winds, and the rate of mass loss affects how they evolve. Massive stars lose enough material through their winds to fundamentally change their structures and lifetimes. Smaller stars like our Sun lose less, but over billions of years, the cumulative effect is still significant. Understanding the mechanisms that drive these winds is essential for understanding how stars age. If switchback-like structures are present in other stars, and there is no obvious reason to think they would not be, then the mechanisms Parker has uncovered may operate throughout the universe. The angular momentum question, raised in an earlier section, deserves another mention here. Parker found that the solar wind near the Sun is rotating more energetically than the models predicted. This means more angular momentum is being carried away from the Sun by the wind, which means the Sun is spinning down faster than previously calculated. Extended over the 4.5 billion years of the Sun's life, this revised rate has implications for how the Sun's rotation has evolved. It also has implications for other stars. The connection between rotation rate, magnetic activity, and stellar evolution is one of the most important relationships in stellar astrophysics. Parker's data is forcing scientists to revisit the assumptions on which that relationship was built. There are also broader implications for plasma physics as a discipline. Plasma is the most common state of matter in the visible universe. Stars are plasma. Nebulae are plasma. The space between galaxies is filled with extremely thin plasma. Understanding how plasma behaves is essential for understanding the universe as a whole. Most of what scientists know about plasma comes from laboratory experiments, theoretical work, and remote observations of astrophysical systems. Direct measurements of plasma in extreme environments have been rare. Parker has provided exactly that. Detailed, high-resolution measurements of plasma in conditions that no laboratory can reproduce. The data is already being used by plasma physicists who have nothing to do with solar physics, applied to problems ranging from fusion energy research to the dynamics of interstellar gas clouds. The closest analogy to what is happening in solar physics right now is the moment in early 20th century physics when experiments began revealing the limitations of classical mechanics. Atoms turned out to behave in ways that Newtonian physics could not predict. New frameworks had to be developed. Quantum mechanics and relativity emerged from the necessity of explaining what experiments were showing. The new theories did not replace the old ones entirely. They contained the old theories as limiting cases, applicable in specific regimes. But they expanded the framework to encompass phenomena that the old theories could not handle. Solar physics may be approaching a similar moment. The existing theoretical framework is not wrong, exactly. It works well for many situations, especially those involving large scales and average properties. But it is incomplete. It cannot capture the small-scale dynamics, the kinetic effects, the multi-scale interactions that Parker is revealing. A new framework, or at least a significantly expanded version of the old one, is going to be needed. What that framework will look like, exactly, is not yet clear. The community is still in the phase of accumulating new data and trying to understand what it means. The theoretical synthesis will come later, perhaps in the next decade, perhaps later than that. There is one more way Parker's discoveries are reshaping the field. They are reshaping the questions scientists ask. Before Parker, the big questions in solar physics were well defined. How is the corona heated? How is the solar wind accelerated? Where do solar flares come from? These were the standard problems, with standard approaches and standard methods of investigation. Parker has not just provided answers to these questions, partial and incomplete as those answers are. It has revealed entirely new questions that scientists did not know to ask. What are switchbacks, really? What produces the heating bursts? What is the structure of the Alfvén critical surface? How does kinetic plasma physics interact with fluid dynamics in the corona? These are questions that did not exist before Parker. They exist now, and they will drive solar physics research for decades to come. The discoveries Parker Solar Probe has made are not abstract findings confined to academic journals. They have direct, practical consequences for life on Earth. Some of those consequences affect technologies we depend on every day. Others affect industries and economies that most people never think about. And a few affect the long-term question of whether human civilization can continue to expand into space safely. The Sun, despite being 93 million miles away, reaches into nearly every corner of modern life. Understanding it better matters in ways that are concrete, measurable, and increasingly urgent. The most immediate practical consequence involves space weather. Solar storms, the violent eruptions of plasma and radiation that the sun produces during periods of high activity can have devastating effects on technological systems. A major solar storm in 1859, known as the Carrington event, produced electrical currents in telegraph wires that started fires in offices and sent shocks through operators. At the time, the world's electrical infrastructure was minimal, and the damage, while dramatic, was limited. A storm of similar magnitude today would have very different consequences. Modern power grids, satellite networks, communication systems, and aviation operations are all vulnerable to the effects of space, whether in ways that 19th century telegraph offices were not. Estimates of the cost of a major solar storm today range from hundreds of billions to trillions of dollars in direct damage and economic disruption. Power grids could be knocked out for weeks or months in affected regions. Satellites, including the constellation of GPS spacecraft that modern navigation depends on, could be damaged or destroyed. Aircraft on polar routes, which lose communication and navigation capabilities during severe space weather events, would have to be rerouted at enormous cost. The economic disruption would ripple outward through every industry that depends on functioning communications, navigation, and electrical infrastructure, which is to say, essentially every industry. The ability to predict and prepare for such storms depends on understanding how solar disturbances propagate from the sun to Earth. Parker's discoveries about the structure of the solar wind, the origins of solar wind streams, and the role of switchbacks in shaping the wind's properties are directly relevant to this prediction problem. The more scientists understand about how the wind behaves near the sun, the better they can predict what it will do by the time it reaches Earth. Improvements in space weather forecasting do not just save money. They protect critical infrastructure that modern civilization depends on. They allow operators to take protective measures before storms hit. They give satellite operators time to safe their spacecraft, power grid operators time to reduce loads, aviation authorities time to reroute flights. Parker's findings about the variability of the solar wind have particular relevance here. The discovery that the slow solar wind has multiple sources, each with different properties, means that space weather forecasters need to consider the source of an approaching storm in addition to its overall intensity. A storm originating from one type of source might have different magnetic configurations, different particle compositions, different interaction patterns with Earth's magnetosphere than a storm of similar size from a different source. The implications for forecasting are still being worked out, but the trend is clear. More accurate predictions require more detailed understanding of where the wind is coming from, and Parker is providing that understanding for the first time. Beyond space weather, there are implications for the growing field of commercial space activity. Companies are launching unprecedented numbers of satellites into low Earth orbit. Mega-constellations of communications satellites, like those operated by SpaceX, OneWeb, and others, now contain thousands of spacecraft, with plans for tens of thousands more. These satellites are vulnerable to atmospheric drag effects that depend on solar activity. When the sun is more active, the upper atmosphere heats up and expands, increasing drag on satellites in low orbits. Several satellites have already been lost to unexpectedly high drag during periods of increased solar activity. The ability to predict how the atmosphere will respond to changes in solar conditions, which depends in part on understanding how the solar wind interacts with Earth's environment, has direct consequences for the satellite industry and for everyone who uses satellite-based services. There is also the matter of human spaceflight. Astronauts in low Earth orbit are partially protected from solar radiation by Earth's magnetic field and atmosphere. Astronauts on longer missions, to the Moon or eventually to Mars, will not have that protection. Solar radiation, particularly during major storms, can be lethal to unshielded humans. The ability to predict storms and provide shelter for astronauts during them is essential for the safety of crewed deep space missions. NASA, the European Space Agency, and other organizations planning lunar and Martian missions are paying close attention to Parker's findings, because the data is directly relevant to the radiation environment future astronauts will face. The implications extend even further. Climate scientists have long studied the connection between solar activity and Earth's climate. The connection is real but subtle. Variations in solar output over the 11-year solar cycle and over longer time scales contribute small but measurable changes in Earth's climate. The exact mechanisms by which solar variability affects climate are still being studied, and they involve not just changes in total solar output, but also changes in ultraviolet radiation, changes in the solar wind, and changes in cosmic ray flux that depend on the heliosphere's structure. Parker's data on the inner heliosphere and the solar wind contributes to this research by providing better understanding of how the sun's output translates into the environment Earth experiences. Better solar physics means better climate models, which means better long-term predictions of how Earth's environment will evolve. There is a deeper implication that goes beyond practical applications. Parker's discoveries are giving humanity its first detailed look at the inner workings of a star. Stars are the engines that drive the universe. They produce the light that makes life possible, the heavy elements that make planets possible, the eventual ends that produce the next generation of stars and worlds. Understanding stars is fundamental to understanding the universe. For most of human history, that understanding was limited by what could be observed from a distance. Parker has changed that, at least for our own star. We can now study a star from inside its atmosphere with detail and precision that no previous mission could approach. This has consequences for how scientists think about other stars, particularly stars that host planets. The discovery of exoplanets has exploded over the past 2 decades. Thousands of planets are now known to orbit other stars, and many of them are in the so-called habitable zones where liquid water could potentially exist on the surface. Whether any of these planets actually harbor life depends on many factors, including the behavior of their parent stars. Stars produce stellar winds that can strip away planetary atmospheres. They produce flares that can sterilize planetary surfaces. They produce ultraviolet and X-ray radiation that can drive complex atmospheric chemistry or destroy it. Understanding how these stellar effects operate in detail requires understanding the stellar atmospheres that produce them. Parker is providing that understanding for the Sun, and the lessons learned will be applied to interpreting observations of other stars. The search for life beyond Earth, in particular, depends critically on accurate models of how stars affect their planets. A planet in the habitable zone of an active star might be uninhabitable because the star's flares constantly bombard its surface. A planet in the habitable zone of a quieter star might be habitable for billions of years, allowing life to develop. Distinguishing between these cases requires detailed models of stellar behavior. Those models start with the Sun. The better scientists understand the Sun, the better they can model other stars. The better they model other stars, the better they can identify which planets are good candidates for hosting life. There is also a more philosophical aspect to Parker's mission. The spacecraft represents one of the few times in human history that we have deliberately sent a machine into an environment where, by all reasonable standards, it should not be able to survive. The Sun has been there for 4.5 billion years. Humans have known about it since before we were human. We have worshipped it as a god. We have studied it as a phenomenon. We have learned to live within the radius of its warmth and to be wary of its dangers. But until Parker, we had never approached it as something to be visited. The spacecraft has done what generations of astronomers could only dream of doing. It has gone there. It has touched the star at the center of our world. And it has come back with data that is changing our understanding not just of the Sun, but of ourselves and our place in the universe. What we do with that understanding in the years and decades to come depends on how we choose to use the knowledge. Some of it will be applied to practical problems, to protecting our infrastructure and our astronauts and our economies. Some of it will be applied to scientific problems, to understanding stars and planets and the universe at large. And some of it, the most important part, will simply become part of who we are, a species that learned what its star was made of by going there, a civilization that, having reached the threshold of its own atmosphere, began to imagine the worlds beyond. The implications of Parker's mission are not only scientific, they are human. Despite everything Parker Solar Probe has accomplished, the most important fact about the mission may be how much it has left unanswered. Every discovery the spacecraft has made has opened up new questions. Every measurement has revealed phenomena that the existing theories cannot fully explain. Every close approach has brought back data that hints at processes scientists are only beginning to understand. The corona has not given up its secrets willingly. It has yielded just enough to make clear how much remains hidden. The first and most pressing unanswered question is the one that drove the mission from the beginning. What heats the corona? Parker has narrowed the possibilities. The data is consistent with a combination of wave heating and reconnection-related processes, with switchback dissipation playing a significant role. But no one can yet write down a complete, quantitative theory of coronal heating that accounts for all the observations. The relative contributions of different mechanisms are not known. The conditions under which different mechanisms dominate are not known. The temperature profiles, particle distributions, and energy balance of the corona are described by the data, but not yet explained by the theory. Solving this problem will require new theoretical work, new computational models, and possibly new physics that has not yet been developed. It is the central challenge of the field for the coming decade. The switchbacks themselves remain incompletely understood. Parker has identified the leading candidate for their origin interchange reconnection near the boundaries of coronal holes, but the details are still being worked out. The exact mechanism by which a reconnection event produces a switchback is not fully characterized. The factors that determine the size, duration, and energy of individual switchbacks are not fully understood. The way switchbacks dissipate as they propagate outward, depositing their energy into the surrounding plasma, has been observed but not modeled in detail. And the question of whether switchback-like structures exist around other stars, and what role they play in stellar wind acceleration throughout the universe, remains entirely open. The answers will require not just more Parker data, but also observations of other stars at levels of detail that current telescopes cannot achieve. The heating bursts that Parker detected during its closest approaches remain among the most mysterious findings of the mission. These brief, intense spikes of plasma temperature have no clear source in any existing theory. They are too brief to be solar flares, as traditionally defined. They are too localized to be explained by large-scale processes. They appear to be a kind of activity that exists in the deepest corona, but has no counterpart in the surface phenomena that scientists can observe from Earth. Whether they represent a previously unknown class of solar events, or a new manifestation of known processes, or something else entirely, remains to be determined. Future close approaches will provide more data, but a definitive understanding may require dedicated theoretical work that has not yet begun. There are also questions about the structure of the corona that Parker's findings have made more pressing. The discovery that the Alfvén critical surface is wrinkled and dynamic rather than smooth and stable raises questions about how that boundary evolves over time. Does the wrinkling pattern change with the solar cycle? Are there configurations of the surface that produce particularly intense space weather effects when they reach Earth? Can the patterns of wrinkling be predicted from observations of the Sun's surface, allowing forecasters to anticipate how the wind will behave before it crosses the boundary? These are questions that require both more Parker data and improved theoretical understanding to answer. The fine-scale magnetic structures that Parker identified during the closest approaches, those coronal eddies and similar features, remain only partially characterized. The team has documented their existence and measured their basic properties, but the dynamics of how they form, evolve, and disperse is still being studied. Whether these structures are a fundamental feature of stellar atmospheres in general or a peculiarity of the Sun's specific configuration is not yet known. They may turn out to be the building blocks of larger-scale phenomena, or they may be a kind of activity that exists primarily in the deepest corona and dissipates quickly as plasma moves outward. The dust environment near the Sun raises its own set of questions. Parker has confirmed the existence of the dust-free zone and mapped its rough boundaries. But the detailed structure of the boundary, the way it varies with solar activity, and the precise processes by which dust is removed from the inner solar system are not fully understood. The dust streams from broken comets, like the C-2019 Y4 encounter described earlier, provide opportunities to study the evolution of cometary debris in extreme environments. But these encounters are rare and difficult to plan for. Building a complete picture of the inner solar system's dust environment will require additional missions and possibly dedicated dust sampling spacecraft. Beyond the questions Parker has raised about the Sun itself, there are questions about what comes next. Parker is not going to last forever. The spacecraft has enough fuel and operational capability to continue its mission through at least 2026, possibly longer. But eventually, the propellant will run out, the equipment will degrade, and the mission will end. The spacecraft will then continue orbiting the Sun indefinitely, but without the ability to communicate or take useful measurements. The data Parker has collected will continue to be analyzed for decades, but no new measurements will be possible after the mission ends. The question is what comes after Parker. NASA and the European Space Agency have begun studying concepts for follow-on missions, though none have been formally approved as of 2026. The leading concept is sometimes called the Solar Polar Imager or Solar Polar Probe. This mission would send a spacecraft into an orbit that takes it over the Sun's poles, regions that no spacecraft has visited since the Ulysses mission of the 1990s. The poles are particularly important because they are the source of much of the fast solar wind, and because the polar magnetic field plays a crucial role in driving the solar cycle. A spacecraft that could observe the poles in detail would provide information that Parker, which orbits near the Sun's equator, cannot obtain. Another concept being studied is a multi-spacecraft mission that would deploy several smaller probes at different distances from the Sun, creating a network of measurements that could capture the dynamics of the inner heliosphere in ways that a single spacecraft cannot. Such a mission would be more expensive than Parker and would require advances in autonomous operations and inter-spacecraft communications. But it would provide the kind of three-dimensional, multi-point measurements that solar physics increasingly requires to test theories of small-scale dynamics and complex magnetic interactions. There are also more ambitious concepts being discussed. Some researchers have proposed missions that would actually fly even closer to the Sun than Parker, perhaps within 1 or 2 solar radii of the surface. The thermal challenges would be even greater than for Parker, requiring new generations of heat shield technology and active cooling systems that have not yet been developed. The science returns from such a mission would be extraordinary, providing direct measurements of the regions just above the Sun's surface where many of the key physical processes originate. But the engineering remains formidable, and no such mission has been funded. In the longer term, there are concepts for missions that would not just observe the Sun, but actively probe its environment. Dropping small payloads into the corona on suicide missions, taking measurements during their final descent, and transmitting data until they vaporize. Sending spacecraft into the solar wind to release traces that could be tracked from afar, mapping the wind's flow patterns in unprecedented detail. Building solar telescopes at the Moon or on other airless bodies, where the lack of atmosphere allows for observations of the Sun that are impossible from Earth. These are speculative concepts at this point, but they represent the future of solar physics if the field can secure the resources to pursue them. There is also the broader question of what other stars are like. Parker has revolutionized understanding of the Sun, but the Sun is just one star among hundreds of billions in the Milky Way galaxy. Other stars have different temperatures, different sizes, different magnetic activity levels, different chemical compositions. The processes Parker has revealed near the Sun must operate somewhat differently around other stars. Whether they operate similarly enough that lessons from the Sun translate directly to other stars, or whether each type of star requires its own detailed study, is not yet clear. The James Webb Space Telescope and other next-generation observatories are beginning to provide detailed observations of stellar atmospheres, and the data is starting to reveal both similarities and differences with the Sun. The full picture will take decades to develop. The unanswered questions, taken together, define a research agenda that will keep solar physicists busy for the rest of this century. Parker has given the field a new starting point. The mission has not closed any books. It has opened them. There is something worth pausing to consider about Parker's solar probe, beyond the data it has collected and the theories it has overturned. Something about what the mission represents. About what it means for a species like ours, evolved on a small rocky planet in orbit around a fairly ordinary star, to build a machine that can travel to that star and survive long enough to send back measurements. About what it says, regardless of the specific scientific findings, that we managed to do this at all. Humans have been looking at the sun for as long as humans have existed, probably longer. Our pre-human ancestors looked at it too. The sun has been the central object in human consciousness, in human mythology, in human religion, in human science, for the entire duration of our species. We have called it Ra and Helios and Sol and Surya. We have built temples to it. We have written hymns about it. We have organized our calendars around its movements, our agriculture around its seasons, our daily lives around its rising and setting. The sun is not just a star to us. It is the star. The one that made us possible. The one whose light, falling on a planet that happened to be the right distance away, allowed photosynthesis to develop, allowed plants to grow, allowed animals to evolve, allowed brains to develop, allowed minds to emerge that could eventually look up at the sun and ask what it actually was. For most of human history, the sun was a mystery that could only be contemplated, not investigated. Ancient astronomers tracked its movements with great care, mapping its yearly path across the sky, predicting eclipses, marking solstices and equinoxes. But they could not say what the sun was made of, how it produced its light, why it shined. The Greeks speculated that it might be a giant ball of fire, or a chariot wheel pulled across the sky, or a hot stone the size of the Peloponnese. The medieval scholars, working from inherited classical and religious traditions, did not advance much further. The sun was the sun. It was studied as a phenomenon, not as a physical object with explainable properties. The scientific revolution began to change that. Galileo, observing the sun through his telescope in the early 1600s, discovered sunspots, the first clear evidence that the sun was not the perfect, unchanging celestial body that Aristotelian philosophy had insisted it must be. The sun had blemishes. It had structure. It was a thing, not just a symbol. Later observations established that the sunspots moved across the sun's face, which meant the sun was rotating. That was another shock to inherited cosmology. The sun was not just a thing. It was a rotating thing, a body with motion of its own, behaving according to physical laws that humans could potentially understand. The 19th century brought spectroscopy, the technique of splitting light into its component wavelengths and analyzing the patterns. By studying the sun's spectrum, scientists could determine its chemical composition for the first time. Hydrogen and helium dominated, with traces of heavier elements. Helium was actually discovered in the sun's spectrum before it was ever found on Earth, hence its name from the Greek Helios. The sun became, for the first time, a chemistry problem. It was something whose composition could be analyzed, whose elements could be identified, whose physical properties could be inferred from measurements rather than assumed from philosophy. The 20th century brought nuclear physics, and with it, the understanding of how the sun actually produces its energy. The proton-proton chain, the fusion of hydrogen into helium at the sun's core, the release of energy that has powered the sun for 4.5 billion years and will continue to power it for another 5 billion or so before the hydrogen runs out and the sun begins its transformation into a red giant. The sun became a physics problem, a system whose behavior could be calculated from fundamental principles, whose properties could be derived from equations describing the interactions of particles and fields. But all of this was understanding from a distance. Scientists could analyze the sun's light, study its spectrum, build models of its interior. They could not actually go there. They could not put instruments into the corona and take direct measurements. The sun remained, for all the progress in understanding, a remote object known only through the light it sent across the gulf of space. Parker's solar probe changed that. For the first time in human history, a machine built by human hands traveled to the sun, not just toward it, to it, into its outer atmosphere, through the boundary of its corona, close enough to sample the plasma at its source. This is worth pausing to appreciate. It is a feat of engineering, certainly. It is a triumph of decades of patient work, of careful design, of incremental advances in materials science and propulsion and navigation and instrumentation. But it is also something more fundamental. It is the moment when a species that evolved looking up at the sun finally went to see it for itself. The moment when the contemplation of the sun, which had occupied every human culture in every era of history, gave way to the direct investigation of it. The moment when the sun became, for the first time, a place that we had visited. The fact that Parker is a robotic spacecraft rather than a crewed mission does not diminish this accomplishment. The spacecraft carries our instruments, our knowledge, our questions. It extends our senses into a region we could not otherwise reach. When the spacecraft measures the magnetic field in the corona, those measurements are, in a meaningful sense, our measurements. When it photographs the dust environment near the sun, those photographs are our photographs. The spacecraft is an extension of human curiosity and human capability, sent to a place that no human body could survive. It is doing for us what we cannot do for ourselves, and what it learns becomes part of what we know. There is a phrase that has been used in the Parker Solar Probe team's communications, particularly in the lead-up to the closest approach in 2024. To touch the sun. The phrase is simple, almost poetic. It conveys the essential character of what Parker has accomplished. Not to study the sun from afar, not to observe the sun through layers of distance, to touch it, to make direct contact, to extend our reach across the 93 million miles that separate us from our star and place an instrument in its atmosphere, to touch the sun. When you consider how vast that distance is, how hostile the environment, how seemingly impossible the engineering, the achievement becomes more remarkable. The sun is the source of nearly all the energy that powers life on Earth. It is the engine that drives our weather, our climate, our seasons. It is, in a very real sense, the reason we exist. And we have now sent something to it. Something that bears our fingerprints, our designs, our intentions. Something that carries our questions out across the gulf of space to the very edge of the star that made us possible. There is a cosmic perspective in this that is easy to miss when discussing the technical details of the mission. From the vantage point of the universe at large, what Parker has done is a small thing. A robotic spacecraft from a single planet has approached its parent star and taken some measurements. The galaxy contains hundreds of billions of stars. Many of them are surrounded by planets. If even a small fraction of those planets have produced technological civilizations, the universe must contain countless examples of species that have studied their own stars in similar ways. Parker is not unique on a cosmic scale. It is one event among many. But from the perspective of this planet, this species, this moment in our history, Parker is an extraordinary thing. It represents the culmination of millennia of patient observation, careful theorizing, and incremental engineering. It is the proof that we are capable, as a species, of doing something genuinely difficult, something that requires sustained effort over generations, something whose payoff is not immediate gratification, but the slow accumulation of understanding. It is evidence that the curiosity that drove the first ancient astronomer to look up at the sun and wonder what it was has not died. It has grown, through countless generations of asking and asking again, into a capability that no previous civilization on Earth could have imagined. The sun does not know we sent Parker. The sun does not know we exist. The sun continues its 4.5 billion year process of burning hydrogen, unchanged and unaware. We are a brief, recent phenomenon on a small planet in its outer regions, and from the sun's perspective, if it had one, we would barely register. But from our perspective, the relationship is everything. The sun is our star. We are its planet. And now, finally, we have reached out and touched it. We walk through the long history of how this mission came to be, the decades of failed proposals, the engineering challenges that defeated multiple generations of designers. The heat shield, just 4.5 inches thick, made of carbon foam and carbon-carbon composite, and a thin white ceramic coating, that turned out to be one of the most remarkable pieces of engineering in the history of spaceflight. The 7 Venus flybys, each one threading the spacecraft past the planet at exactly the right angle and speed to steal a fraction of orbital energy and pull Parker closer to the Sun. The instruments, designed to operate in an environment that would melt steel, that worked exactly as designed and returned data of unprecedented quality. We saw what scientists believed about the Sun before Parker launched. The layered model of solar structure, with its tidy progression from core to corona. The two main theories of coronal heating, wave heating, and nanoflares, competing for decades without a clear winner. The mystery of solar wind acceleration, with multiple candidate mechanisms but no definitive answer. The assumption that the magnetic field structure of the corona was relatively smooth on large scales, with turbulence confined to small features. The belief that the field of solar physics was largely understood, with only details remaining to be filled in. And we saw what Parker found. The switchbacks, those violent S-shaped reversals in the magnetic field that nobody had predicted, present in such numbers and carrying such energy that they may be fundamental to how the Sun connects to its solar wind. The Alfvén critical surface, the boundary that marks the true edge of the Sun's atmosphere, found to be wrinkled and dynamic rather than smooth as the models had assumed. The dust-free zone, a clear region near the Sun where microscopic particles cannot survive, with a boundary sharper than theory had predicted. The Mercury dust tail, an entirely new feature of the inner solar system that no spacecraft had ever observed. The heating bursts, brief and intense and unexplained, occurring in the deepest corona where the heating problem is at its most acute. The reheating of the solar wind in regions where no heating mechanism should exist. The kinetic effects in the plasma that suggest the standard fluid descriptions of the corona may be inadequate. The fine-scale magnetic structures revealed during the closest approach in December 2024, structures that may represent a new class of stellar atmospheric phenomena. Each of these discoveries has changed the field of solar physics. Together, they have forced a fundamental reconsideration of how scientists think about stars. The Sun, the most studied object in astronomy, has turned out to be doing things that no one expected. And the data that Parker has returned is not just refining the existing theories. It is challenging them at the foundations. We considered what these findings mean for humanity. The practical consequences for space, whether forecasting, satellite operations, power grid protection, and the safety of astronauts on future missions. The implications for the search for life on planets around other stars, where understanding stellar atmospheres is essential to interpreting what is observable from Earth. The deeper implications for plasma physics as a discipline, with data from a regime that no laboratory can reproduce. The connection to climate science, where solar variability plays a role that remains incompletely understood. We also considered what remains unanswered. The complete theory of coronal heating, still being worked out. The detailed mechanisms behind switchback formation and dissipation, still under active investigation. The mysterious heating bursts, with no clear source in any existing theory. The structure of the inner heliosphere, mapped in unprecedented detail by Parker, but still incompletely understood. The future missions that will build on Parker's discoveries, including concepts for spacecraft that would visit the Sun's poles, fly even closer to its surface, or deploy multiple coordinated probes to capture the dynamics of the inner solar system in ways a single spacecraft cannot. And we pause to consider what Parker represents beyond its specific scientific findings. A species that evolved looking up at the Sun has finally sent something to visit it, not from afar. Not through the filter of telescopes and remote sensing, directly into the atmosphere of the star itself, to touch the Sun. After thousands of years of looking up, of wondering, of contemplating, of building theories that could only be tested from a distance, we built a machine that could go there. And it went. And it survived. And it sent back data that has changed how we understand the star that made us possible. The Parker Solar Probe mission will continue for years yet. The spacecraft has more close approaches planned through 2026 and possibly beyond. Each pass will return more data, Each dataset will reveal new features, raise new questions, push the boundaries of what scientists can understand about the sun. The team continues to work, continues to analyze, continues to publish papers that change the textbook picture of how stars work. The discoveries are not finished. They are only beginning. There is something profound about a mission that has answered some of the longest-standing questions in solar physics while opening up entirely new categories of mystery. Parker has not solved the sun. It has shown that the sun is even more complex, more dynamic, more interesting than scientists had imagined. The corona is heated by mechanisms that interact in ways the existing theories cannot fully describe. The solar wind is accelerated by processes that involve countless small magnetic events combining into the smooth outflow that fills the heliosphere. The structure of the inner heliosphere is shaped by phenomena that operate on scales no previous spacecraft could resolve. And there are still things in Parker's data that no one knows how to explain, measurements that the most experienced solar physicists in the world look at and admit, honestly and openly, that they do not yet understand. This is the spirit of exploration at its best, not the certainty of confirming what we already know, but the humility of discovering what we do not. Not the satisfaction of completing a picture, but the excitement of finding new pieces that demand to be added. Not the closing of questions, but the opening of new ones, each more interesting than the last. Parker has shown us that even the star we know best, the star that has been studied for centuries, the star that powers our world, is still full of surprises, still capable of revealing things we never anticipated, still able to humble the theories we have spent generations building. A spacecraft the size of a small car, with a heat shield barely 4.5 inches thick, traveling at 430,000 miles per hour, 3.8 million miles from the sun, carrying instruments designed by patient generations of engineers and scientists, sending back data that is rewriting the textbooks, touching the star that made us possible and showing us that even there, even in the place where life on Earth originates, the universe is more mysterious than we knew. The Parker Solar Probe will eventually fall silent. Its propellant will run out. Its instruments will degrade. The closest passes will end. But the spacecraft will continue orbiting the sun for as long as the sun exists. It will be there, a small machine made by humans orbiting our star, a permanent monument to what our species accomplished when it finally reached out and touched the source of all our days. The story of Parker is not yet finished. The discoveries are still arriving. The mysteries are still deepening. The questions are still expanding. And somewhere in the data, in the measurements that have not yet been fully analyzed, in the patterns that researchers are only beginning to recognize, there are almost certainly more surprises waiting. More phenomena that no one anticipated. More clues to how the universe actually works. More reasons to keep looking, keep asking, keep building machines that can go where we cannot go ourselves. That is the legacy Parker Solar Probe has already secured. Not just the specific discoveries it has made, but the demonstration that we can do this. That a small, persistent, curious species on a small planet around a fairly ordinary star can build machines that visit that star and come back with knowledge. That the impossible engineering problems of one generation can become the routine accomplishments of the next. That the questions we ask today will lead, sometimes after decades of patient work, to discoveries that change everything we thought we knew. If this story has moved you, if you find yourself drawn to the mysteries that lie at the edge of human understanding, take a moment to like this video and subscribe to the channel. It is a small action, but it helps this work reach more curious minds. Share this with someone who looks up at the sky and wonders. Tell us in the comments what part of the Parker mission left the strongest impression on you and where in the world you are watching from tonight. We love seeing how far these stories travel. Until next time, keep looking up. The universe is more remarkable than we know. And somewhere out there, in the data not yet analyzed, in the missions not yet launched, in the questions not yet asked, the next great discovery is waiting.